So these are the lecture problems for Chapter 8. Take a second to read the problem. This is really just to get familiar with working with converting between RPMs and radians per second, as well as converting between linear speed and acceleration and angular. So here I have a grinding wheel that is rotating at some angular velocity. I'm given that in revolutions per minute, and I'm asked to convert it into radians per second. So the angular velocity is going to be 2200 revolutions per minute. I know that in one revolution there are 2 pi radians, and I also know that in 1 minute there's going to be 60 seconds. So my revolutions are going to cancel out, my minutes are going to cancel out, and I'm going to end up with my angular velocity to be 230.4, and the units are going to be radians per second. Now I'm asked to find what the linear speed and acceleration are at a point at the edge of the grinding wheel, so maybe perhaps a point right here. I'm told that the diameter of the grinding wheel is going to be 0.35 meters. That tells me something about the radius. It tells me the radius is half of that, or 0.175 meters. Simply, I'm looking at equations 8.84 and 8.6. I can write the linear velocity in terms of the angular velocity and the radius. So 230.4 radians per second multiplied by 0.175, I find out that the linear velocity is going to be about 40 meters per second. Similarly, the linear acceleration is going to be the angular velocity squared multiplied by the radius, so 230.4 radians per second, quantity squared, multiplied by 0.175 meters, and I'm going to come out with 9,300 meters per second squared. So that's quite a few g-forces that's being felt by an object at the edge of the wheel. Take a second to read 25. What I'm looking at, or what I need to calculate, is the net torque on this wheel. That net torque is going to be the torque of all of these forces that are involved, and I know that there's going to be a frictional torque as well, so a torque due to friction. To calculate what the torque is from all of these forces, I'm going to say that this is going to be force 1, this is going to be force 2, and this is going to be force 3. That's going to be torque 1 plus torque 2 plus torque 3. And what I'm going to do is I'm going to define the counterclockwise direction to be positive for all of my torques. So torque number 1 is going to apply a counterclockwise torque that's going to be equal to the force, 28 newtons, multiplied by the distance, which is going to be 0.24 meters. Torque number 2 is going to apply a clockwise torque, so I'm going to put a negative sign. The force is 18 newtons. The distance that's applied over is 0.24 meters. And last but not least, the 35 newton force number 3 is going to also be in the clockwise direction, so it's going to be a negative torque that's equal to 35 newtons multiplied by the 0.12 meters that force acts over. So when you add all these guys up, I'm going to come up with a torque due to my forces of negative 1.8 Newton meters. I know that my frictional torque is going to oppose motion, so that torque is going to be in the positive direction, and it tells me that that's going to be 0.6 Newton meters. Now I have everything that I need to solve for my net torque. I've got a negative 1.8 Newton meters plus my 0.6 Newton meters. So the net torque on this wheel is going to be negative 1.2 Newton meters. All the negative means is it's going to be in the clockwise direction. So make sure you indicate clockwise or counterclockwise when we're talking about torques. So first take a second and read the problem. What we're looking at is a merry-go-round that is accelerating due to a torque. So that immediately says this is most likely Newton's second law, where we're going to write the sum of torques being equal to the rotational mass multiplied by the angular acceleration, and the only torque is going to be the torque due to the dad. So I'm just going to simply write a torque and not have any other subscripts to worry about. So this is what I am trying to solve for torque. I need to know the angular acceleration of the merry-go-round and the rotational mass of the merry-go-round. So let me take a look at this. I know that it's starting from rest, so it originally has no rotation, so 0. I know it's going to spin up to 15 revolutions per minute. Obviously I can't work in revolutions per minute, so I need to convert this guy into radians per second. So 1 revolution is 2 pi radians, and of course 1 minute is going to be 60 seconds. Go ahead and I come up with 1.57 radians per second, and I know the time that it takes to spin up is going to be 10 seconds. So what I can do is I can say, okay, I know that omega is going to be equal to initial omega plus the angular acceleration multiplied by time, and this guy here goes out to be 0, so simply the angular acceleration is going to be the angular velocity divided by time, or 1.57 radians per second divided by 10 seconds, and now I have my angular acceleration is going to be 0.157 radians per second squared. Now to figure out the rotational mass of the system here, if I remember correctly, the rotational mass is going to be the sum of the mass multiplied by their radius, their distance away from the center, the point of rotation, squared. What I can do is, here I have a slightly more complicated than usual system. Here I have a disk, and this disk is going to have a mass big M, and I'm putting 2 children on this disk. Each of these guys is going to have little m, and each one of those children is going to be a distance r away from the center. What I can do is I can break this sum up to represent the disk, so mr squared. So I'm going to say this is of my disk, or my merry-go-round, and now I'm going to have the children. I'm just going to pull them off to the side here. The reason why I'm doing that is because I can go ahead and I can look that guy up. That's going to be 1/2 mass of the disk multiplied by the radius of the disk, or in this case merry-go-round, and that's going to be radius squared. Now I can treat the children separately. I know that I'm going to have two children, each at radius big R away from the center of the merry-go-round, and each with mass m. So I'm going to have two children with mass m located at a distance r away from the merry-go-round. So I can go ahead and I can calculate my rotational mass here. So it's going to be 1/2 multiplied by the mass of the merry-go-round. That's going to be 560 kilograms. The radius of this guy is going to be 2.5 meters. Square that. And I'm going to add 2, multiply that by the mass of the children, 25, and another 2.5 squared. So I'm going to come up with a rotational mass that is equal to 2062.5. Now I know everything that I need to solve for the torque. The torque is going to be the rotational mass, so 26.5 multiplied by the angular acceleration, which is going to be 0.157 radians per second squared. And at the end of the day, I'm going to come up with a torque of 323.98 Newton meters. Now the last thing that I need to do is I need to calculate how much force this guy is. And I know a relationship between force and torque. If I know what the radius is, which I do, I know that the torque is going to be the force in the perpendicular direction multiplied by the radius, and I'm kind of assuming that the man is going to, well, no, I'm not assuming, I'm told that dad pushes tangentially, so all of the force is going to be perpendicular, which is good. So I can solve this guy for the force perpendicular, which is the force of the man. That's going to be 323.98 divided by the radius of 2.5 meters, and I'm going to get the force of the man to be 129.6 newtons. It's going to be my force. So pause for a second and read the problem. It's an energy conservation problem where I'm looking at these 2 points, A and B, and what I'm going to do is I'm going to say the energy at A is equal to the energy at B. At point A, the ball is not moving, it's not rolling. All it has is some mass times gravity times height. At point B, it's going to be rolling. It's going to have some translational energy associated with its motion. So 1/2 mv squared is the translational energy. It's also going to be rolling. It's going to have some rotational energy as well. So 1/2 I omega squared. And it also tells me that it is rolling without slipping. So that's kind of a key word of saying that the rotational velocity must be equal to the linear velocity divided by the radius of the ball, little r here. So let's take a look at first the height of this guy. You might intuitively say that the height of this guy is going to simply be the radius of the big curve right here. However, remember that we're talking about large bodies, and we treat large bodies about their center of mass. So here is the center of mass of that ball, and you can kind of see that it is going to be off the deck a little bit. So if I defined right here to be equal to my 0 point, then I'm still going to have some potential energy over here in B. So what I'm going to do is I'm going to choose my 0 point to be where the center of mass of this guy is when the ball is at point B. So here's going to be my 0 point. I know that it is offset from the ground simply by the little radius r, so my height right here is going to be big R minus little r. So I can simply write this guy as mass times gravity times big R minus little r. Now I can rewrite the rest of this guy, 1/2 mass velocity squared, and I can go and I can look up the moment of inertia for a ball. So let's go ahead and do that. So I'm going to say 1/2 multiplied by my moment of inertia, which is going to be 2/5 multiplied by the mass of the ball multiplied by its radius squared. And then I'm going to take my expression for angular velocity right here and put that in right here all in one big step. So here I'm going to have velocity divided by radius and the whole quantity squared. Now this may look like a big nasty equation, however I can go ahead and I can cancel my masses out. I can take this radius squared and cancel that guy out with this guy. And lastly, I can cancel that 2 out with this guy. So what I'm left with is g big R minus little r is equal to 1/2 velocity squared plus 1/5 velocity squared. I can very easily add 1/2 plus 1/5. That's going to give me 7/10 of the velocity squared. I'm solving for velocity, so I simply write velocity is going to now be equal to 10 times gravity, big R minus little r. Don't forget my 7, and take the square root of this guy. So here I have came up with an expression for the velocity at the lowest point in the track rolling without slipping.